Section: Introduction. In this section, we discuss the advancements of multimodal large language models, MLLMs, in tackling various vision language tasks. Despite significant progress, challenges related to compositionality persist, as seen in models like LLaVA, Cambrian, and Eagle. For instance, when posed with the question, "Are there more blue squares or red circles in the image?" a model that can identify shapes, colors, and count objects should provide a correct answer. However, even the latest models struggle with such complex questions, succeeding only with simpler ones, like, "What color is the square?" This indicates that current models do not effectively generalize to tasks that require higher compositional complexity. To tackle this issue, recent efforts have focused on increasing the amount of training data for visual instruction tuning, VIT, which is crucial but resource-intensive for MLLM training. Unfortunately, datasets like LLaVA 665K mainly consist of simple queries that only test one capability, lacking the necessary compositional complexity. Even with extensive instruction tuning, models still face difficulties in integrating capabilities and generalizing to complex visual tasks due to the limitations of their training data. We propose a solution. Instead of merely increasing data volume, we advocate for enhancing compositional capabilities in MLLMs through hierarchically structured training data. We introduce COMPACT, which stands for Compositional Atomic to Complex Visual Capability Tuning. This method allows us to scale MLLM capabilities from basic to more complex levels by defining 10 atomic capabilities and combining them to create a training dataset that helps models understand the compositional structures of complex tasks efficiently. Our key contributions include the introduction of COMPACT, which builds complex capabilities from simple atomic ones. By systematically combining these atomic capabilities, we address a significant limitation of traditional VIT methods that rely on incidental capability composition through data scaling. We also develop a structured data recipe that ensures a balanced distribution across various levels of compositional complexity, covering a broader range of task types. This approach helps flatten the complexity cliff found in conventional VIT datasets, where most questions require only 2 or fewer capabilities. We demonstrate the effectiveness of COMPACT, showing that with just 10% of the VIT dataset size, our method matches the performance of full-scale VIT. Additionally, it shows remarkable generalization to more complex tasks, significantly improving scores on benchmarks like MM* and MM-VET for tasks requiring 4 capabilities. In terms of related work, we highlight the importance of visual instruction tuning, VIT, in adapting MLLMs to respond to various question formats. While VIT has improved general multimodal capabilities, it can limit the quality of responses by focusing too much on response formatting. Our data recipe explicitly models compositional capabilities, addressing the lack of exposure to complex questions during training. We also discuss the concept of compositionality, which refers to how the meaning of complex statements arises from the combination of simpler components. In MLLMs, compositional capability means performing complex tasks by integrating multiple basic visual concepts. Although some studies have shown that MLLMs exhibit signs of compositional capability, they often struggle with combining components effectively. Finally, we touch on data efficiency in MLLMs, noting that VIT is resource-intensive. Research indicates that MLLMs can achieve strong performance with less data through better techniques. Our COMPACT approach formalizes atomic capabilities and incorporates their combinations into the training dataset, efficiently addressing the challenges of generalizing to complex compositional tasks without simply increasing data volume. Section Summary. In this section, we highlight the ongoing challenge of compositionality in multimodal large language models, MLLMs, where even state-of-the-art models struggle with complex queries despite success with simpler ones. We introduce COMPACT, a structured training data approach that systematically combines atomic capabilities to enhance model performance on complex tasks without merely increasing data volume, demonstrating significant improvements in generalization to higher complexity tasks. Section: Method. In this section, we propose COMPACT, a method that enhances the capabilities of multi-level language models, MLLMs, from basic to more complex tasks. We begin by defining atomic visual capabilities, which are the essential skills needed for more complicated visual tasks. For instance, to determine how objects of different colors are arranged, a model must recognize objects, understand colors, and grasp spatial relationships. For each task, we identify a set of atomic capabilities necessary to complete it, defining the number of these capabilities as the task's compositional complexity. Our aim with Compact is to raise the average compositional complexity of our dataset and ensure a balanced distribution of samples, so each question requires the model to combine multiple atomic capabilities during training. We create a taxonomy of these atomic capabilities based on existing research, eliminating infrequent and non-visual skills, resulting in 10 focused capabilities. We categorize these into 3 main groups. 1. Attribution, identifying visual properties like color and shape. 2. Recognition, detecting and interpreting visual entities, including objects and actions. 3. Relation, understanding how entities interact or relate to each other, either spatially or conceptually. Next, we outline our 4-step data recipe for generating high-quality training data that integrates multiple visual capabilities. 1. Capability sampling. We randomly select images and sample a few capabilities from our pool for each image, ensuring diverse combinations and avoiding duplicates. 2. Conversation generation. For each combination, we prompt a model to create a question-answer pair that naturally incorporates all selected capabilities, while adhering to specific constraints to ensure clarity and relevance. 3. Quality verification. We implement a verification process to filter out low-quality questions and ensure that each question requires the exact number of specified capabilities. This process is repeated until we gather enough high-quality conversations for each image. 4. Dataset assembly. Our final dataset combines a small portion of an existing dataset with our generated compositional data. This blend helps maintain the model's ability to handle various response formats while also training it to reason about multiple visual aspects in complex questions. By preserving the original images in our dataset, we can effectively compare Compact with existing methods in extracting detailed information. We also explore how the ratio of the existing dataset to our compositional data impacts performance, aiming to find the best balance between instruction following and compositional capability training. Section Summary. In this section, we propose Compact, a method that enhances the capabilities of multi-level language models, MLLMs, by generating high-quality compositional training data through a 4-step process that integrates atomic visual capabilities. We define atomic capabilities as foundational skills necessary for complex visual tasks and outline how our approach systematically samples, generates, verifies, and assembles data to improve the model's ability to reason about multiple visual aspects in a single question. Section: Experiments. In this section, we evaluate the baseline methods in our Compact approach using existing multimodal benchmarks. First, we outline our evaluation setup and the benchmarks we used. Next, we compare the performance of Compact with relevant baseline models, including LLAVA 665 KVIT. We then analyze how well the Compact-trained model generalizes across different levels of compositional complexity and examine how the distribution of training data affects performance. Finally, we conduct ablation studies to explore various aspects of Compact's design, such as the distribution of compositional complexities and the balance between instruction and compositional tuning data. For our evaluation testbed, we trained the LLAVA 1.5 to 7b LoRa model using a pre-visual instruction tuning checkpoint on our Compact training dataset, which includes 32,000 samples of compositional tuning data. We also incorporated 5% of LLAVA 665K to maintain instruction following capabilities. The model was trained for 1 epoch using the official fine-tuning settings. We compared our Compact data recipe against several baseline datasets, training models with the same architecture and configurations. The LLAVA 665K dataset, which contains 665,000 samples, serves as our main performance baseline. We also used a random subset of 65,000 samples from LLAVA665K to control for data volume, and an icon subset of the same size, selected for its informative samples. We evaluated the models on established multimodal benchmarks that assess complex visual capabilities. These include tasks related to recognition, OCR, knowledge, language generation, spatial awareness, and math. We also looked at benchmarks that focus on visual comprehension skills and open-ended visual question answering. Overall, our results show that COMPACT performs comparably to the LLAVA665K baseline. Our training dataset, which is only 10% of the full VIT data, combines 32,000 compositional tuning samples with 5% of LLAVA665K data. COMPACT outperforms both the random and icons baselines on most benchmarks, achieving significant improvements in tasks like MVET, MM*, InfoVQA, and SeedBench 2+, while remaining competitive in others. We also examined the data efficiency of COMPACT by analyzing how performance changes with varying amounts of compositional tuning data. As we increased the number of compositional samples, we observed consistent performance improvements across all benchmarks. In contrast, the random baseline showed mixed results. Notably, models trained on smaller amounts of compositional data often outperformed those trained on larger random datasets, demonstrating that COMPACT utilizes training data more effectively. We believe this data efficiency stems from two main factors. First, COMPACT balances the distribution of compositional complexity, providing more frequent learning signals for higher complexity tasks. Second, it introduces diverse combinations of capabilities during training, unlike the LLAVA665K VIT, which focuses mainly on simpler tasks. Section Summary. In this section, we evaluate the performance of our COMPACT approach against baseline models on various multimodal benchmarks, demonstrating that COMPACT, trained on a smaller dataset, outperforms both random and icons baselines while maintaining competitive results on complex tasks. We also analyze the data efficiency of COMPACT, showing that it effectively utilizes compositional tuning data to enhance model performance across different benchmarks. Section Analysis. In this section, we analyze the performance gains of COMPACT on complex compositional questions, highlighting its strong potential for compositional generalization. Our results show that COMPACT performs competitively on the MVET and MM* benchmarks, even at higher levels of compositional complexity, despite not being specifically trained on data with complexity greater than 3. For instance, when the complexity is 4, COMPACT scores 57.5 compared to LLAVA665K's 32.5, and at 5, it scores 20.0 versus LLAVA665K's 0.0. This indicates that COMPACT is robust in handling more complex tasks. We also examine the distribution of visual capabilities required to answer questions using GEMINI 2.0 Flash. Analyzing 5,668 questions from the LLAVA665K VIT dataset, we find that the average compositional complexity is about 1.5, with most questions requiring only 1 or 2 capabilities. This scarcity of higher complexity questions in the dataset leads to a drop in performance for tasks that demand compositional generalization. Interestingly, a small number of questions require as many as 10 capabilities, while some require none. Next, we conduct ablation studies to explore key design factors in COMPACT, using a small portion of the LLAVA665K VIT data and a larger set of compositional tuning data. We first assess how a balanced distribution of compositional complexity in the tuning data affects performance. When we create an unbalanced dataset that mirrors the LLAVA665K distribution, we see that COMPACT's performance drops significantly compared to when it is trained on balanced data, confirming that a fair representation of higher complexity samples is crucial for performance gains. We also analyze the importance of different atomic capabilities by excluding specific ones and observing the impact on performance. Our findings reveal that scene understanding and spatial relationships are particularly critical, while capabilities like shape attribution have a lesser effect. To further understand the impact of compositional complexity range, we generate different sets of tuning data with varying complexities. We find that models trained on a broader range of complexities perform better on multi-capability benchmarks, demonstrating that exposure to diverse compositional patterns enhances the model's ability to tackle complex tasks. Lastly, we investigate how the ratio of instruction tuning data affects performance. By gradually increasing the amount of instruction data from the LLAVA 665 KVIT dataset, we observe that performance improves significantly up to a certain point, with diminishing returns beyond 5%. This suggests that a balanced mix of instruction and compositional tuning data is optimal for achieving high performance, indicating that instruction-following capabilities can be developed with minimal instruction data. Section Summary. In this section, we demonstrate that Compact shows significant performance improvements on complex compositional questions, achieving competitive results on benchmarks like MVET and MM*, even generalizing well to higher compositional complexities not seen during training. Our analysis reveals that a balanced distribution of compositional complexity in training data and the inclusion of essential atomic capabilities are crucial for enhancing the model's performance on multi-capability tasks. Section Discussion. In this section, we discuss our findings and their implications. We highlight the significance of our results and how they contribute to the existing body of knowledge. We also consider the limitations of our study and suggest areas for future research. By reflecting on our work, we aim to provide a clearer understanding of the topic and encourage further exploration in this field.